and 6 do not appear at all. Okay, so I'm interested in computing this probability. What is the probability that 1 appears thrice, 2 appears 2 times, 3 also appears 2 times, 4 appears 1 time, 5 appears 1 time, and 6 appears, what do you call, none of the time, because 3 is 2, 4, 7 and 2, 9, yes. So in the 9 tries, the 6 does not appear. So what would be this probability? So you're going to do that. Okay, let's choose 9 and multinomial coefficient, choose 3, 2, 2, 1, 1, 0. Okay, and each one of them has a what you call equal probability. So the 1/6 power 3 times 1/6 power 2 times 1/6 power 2 times 1/6 power 1 times 1/6 power 1 times 1/6 power 0. So this is what that you're going to get, and if you calculate it, it's going to be 9 factorial by 3 factorial, 2 factorial, 2 factorial, 1 factorial, 1 factorial, and 0 factorial. This is going to be 1 times 1/6 power 9 actually. So this is what is going to be the probability of happening of this event. Okay. So this is one example of having multinomial distribution actually. By the way, you can also have, think about it. So using the Bernoulli trial, we had multinomial distribution, binomial distribution, geometric distributions, Poisson distribution, hypergeometric distribution, negative binomial distribution. All these distributions has a link with what do you call, are defined in the terms of the Bernoulli trials or the Bernoulli random variables. So what you can do is that, one thing, and that would be an interesting exercise basically, that take a trial, take a multinomial trial, in other words, in which there are R outcomes. So what would be, so as we have kind of had a multinomial distribution, try to have a version of a multinomial, for example, geometric distribution, or try to have a multinomial, what do you call, Poisson distribution, or their multinomial versions. The first thing would be, would that make sense in multinomial sense? I mean, if they, what would be their distributions actually? Or what would be their formulas? So I think you can also think of writing it actually. Let's move ahead and let's get to, what do you call, the case when you have the independent random variable. So next is that, okay, I have two, so we have talked about, for example, 2 independent events, but now I would like to define what would be the meaning of having 2 independent random variables actually, which is really the generalization of independence of events actually. Two independent random variables. And you see that once you have independent random variables, their joint PDF and joint CDF has a particular form which is easy to determine. Okay, and it's fairly easy to deal with things that you have. It's fairly easy to determine the probabilities actually. Okay. So here's a definition. So I'm going to say that x and y are two independent random variables if what happens? If for any two sets A and B, probability that x would be in set A and y would be in set B is equal to, so this is what? So this represents the probability that, so that's an event, that probability that x is in A intersection probability that y is in B. So that the probability of the intersection should be equal to the product of the probabilities. In other words, the probability that x is in A and the probability that y is in B should be equal to the probability that x belongs to A times the probability y belongs to B actually. Okay? B actually. You can also write it as that if you have this event A, which is really x belongs to A, and event say B, which means that x belongs to B, then probability that x belongs to A and x y belongs to B is basically what you call the probability of EA intersection EB. And if two random variables are independent, then these EA and EB events should always be independent actually. So in other words, this should be equal to probability of EA times the probability of EB, which is same as this. Okay, which is same as this. Let's think about the joint CDF. In particular, if I take minus infinity to A as A and B as minus infinity to B, and I consider what is the value of f of AB, then I know that this is by definition means x less than or equal to A and y less than or equal to B, which is same as probability that x belongs to A, where A is minus infinity to A and y belongs to B. But if x and y are independent, this probability should be equal to the probability x belongs to A times the probability that y belongs to B. And what is the meaning of probability that x belongs to A? It means that probability that x is less than or equal to A times the probability that y is less than or equal to B. But what would be this mean? So this is really the CDF of x evaluated at A and the CDF of y evaluated at B actually. So in other words, f of the joint CDF is really the product of the CDF. What do you call the product of the CDF actually? Okay. The joint CDF is the product of the marginal CDFs, or the individual CDFs of x and y. Okay, so this is what it is going to be. But I know that f of AB, if I want, say for example, joint PDF, so what can I do? I can take this f of AB and differentiate it, say for example, first with respect to A and then with respect to B. So take, say, derivative of this with respect to A first and then derivative with respect to B. So it's going to be fx of A times fy of B. So the derivative of this with respect to A, so this is independent of what you call A. So the derivative of this with respect to A is going to be small fx of A and then derivative of fy of b with respect to b is going to be what you call small fy of b actually. So this is another interesting thing that you can observe from what do you call the joint CDF, that if you have two independent random variable, then the joint PDF of such two independent random variable is equal to the product of the PDFs of the random variable x and the PDF of random variable y actually. Okay. The joint PDF is product of the marginal PDF of x and the marginal PDF of what do you call b. So this is what is going to be the interesting case actually. Let's do one example. So consider n plus m Bernoulli independent Bernoulli trials. Independent Bernoulli trials. So that's an example of two independent random variables. Okay. N plus m Bernoulli trials. So with success as p. Okay, so that success probability is success probability p. Now consider the x. X represents the number of n number of successes, okay, in first n trials, okay, and y represents the number of successes in last m trials. Okay, so in first n trials, x represents the number of successes, and in last x trials, m trials, y represents the number of successes. So what values x can take? So x can take, I know, 0, 1 and up to n, and y can take 0, 1, 2 and up to what we call m. Now if I ask from you what is the probability that you have x successes in first n trials and y successes in last m trials? Okay. So how you can compute it? So you can compute it as the probability. So x successes in first m trials, and so it's like x successes out of n trials and y successes out of m trials. So what is x successes out of n trials? So it's going to be, since all of these are independent, so it's going to be n choose x, p power x, 1 minus p power n minus x. And y successes out of m trials, last m trials. So m choose y times p power y and 1 minus p power n minus what do you call 1 minus p power n minus x power, what do you call y, n minus y actually. Okay, so this is equal to if you see, I can write this as the probability of x equal to x, where x being a binomially distributed random variables, okay, taking values n times the probability of y equal to y, where y is a binomially distributed random variable taking m values. Another example that you can, for example, solve through independence of random variable. So imagine that there are two people, so one is male and one is female. Okay, so there are two people who decide to so a male and a female decide to meet at a location, maybe some park or something like that. Okay, or maybe in an office or any place. So they want to meet at a location between, say, 12 of noon to 1 p.m. So 12 noon, between 12 of noon to 1 p.m. actually. Okay, so they want to meet between this time interval. Now imagine that male and female can come in the park at any time between 12 to 1. Okay, so they can come at any time. So both can arrive at any time in this interval. Okay. Imagine you want to know that what is the probability that if one of them arrives at some moment at the park, he has or she has to wait, because one who can arrive could be male or could be female. Okay, so the one who arrives at the fixed location or in the park, for example, at any time between 12 to 1 p.m. but he or she has to wait for 10 more minutes for other person to arrive actually. Okay, for other person to arrive. So it could be the situation that man arrived at, for example, 12:15. What is the probability that the male has to wait for more than 10 minutes for women to arrive, okay, for the girl to arrive? Or the female can arrive at any instant between 12 to 1 p.m. What is the probability that she has to wait for the men to arrive, or for the male to arrive more than 10 minutes actually? So this is what that we would like to do. So let's x denote the time in minutes when time in minutes past 12. Okay. In minutes past 12, means after 12, when man arrives or the male arrives at the location, and y denote the time past 12, after 12, when female arrives. When female arrives, okay? Alright. So, what I would like to say, imagine that both arrive at independently. Okay? So their arrival do not depends on each other. So in other words, x and y are independent templates. So both arrive at independent times. Question. First of all, what would be the distributions of x and y, by the way? So the male can arrive at any time between 12 to 1 p.m. So this means that x is uniformly distributed. So x is uniformly distributed between 0 to 60. Between 0 to 60. And y is also uniformly, because she can also arrive at any time between 0 to 12 to 1. So, you know, it's also so y has also a uniform distribution, okay, with the parameters 0 and 60. So what would be the PDF for fx of x? So it's going to be 1 over 60 minus 0, 1 over 60, when x is between 0 to 60 and equal to 0 otherwise. Okay. Similarly, fy of y, the PDF of this is going to be 1 over 60 when y is between 0 to 60 and equal to 0 otherwise. So what was the question that? What is the probability that if one person arrives at a park at some moment between this interval, he or she has to wait for more than 10 minutes for other person to arrive actually. So in other words, I have to compute the probability that, what is the probability that he arrives at time x, but he has to wait for more than 10 minutes for arrival of the y actually. Or maybe the arrival time of x is more than 10 minutes than the arrival time of the y actually. Or what could be the other situation? That y plus 10 is what you call bigger than x actually. So this is what that we need to compute. So let's compute it.